As you can see from the heading here, we're going to be looking at the potential inside a hollow conducting charged sphere. Before we get to that though, we'll talk about a few other bits and pieces along the way, and we'll eventually get to what that potential looks like. As we do that though, I want to just draw your attention to a few things as we go through. And I'll stop using this full term hollow conducting charged sphere, but to start with, if we look at a conducting charged sphere, it's going to have its charge evenly distributed across the surface. When we say charged, we basically mean that we've either got an excess of electrons or a lack of electrons. We'll just deal with a positive charge, so a lack of electrons, for the purposes of what we're looking through here, but it equally applies if you've got a negative charge there as well. So the reason why it's going to be over its surface, first of all, if it's a conductor, means that charges can move freely through the substance. So if we then have a look at this scenario, so imagine that this is a cross section of our charge conducting sphere. So what we will see is that the charge is going to build up across the surface, and it will be on the outside, more to the point as well. Now, to explain why that is, a couple of things to keep in mind. In order to explain that charge separation, the first thing to identify is that charges will move until they are as far apart as possible. And secondly, on top of that, in terms of that moving, they will continue to move until they are in equilibrium. And by that we mean that the forces on each of the charges are balanced. So in this sort of arrangement where they're equally spread across the surface of the conductor, that's when they'll be in equilibrium, when the charges are all evenly distributed. So the next thing to be aware of here is that the electric field lines will always exit the surface, electric field, they'll always exit the surface of a conductor at 90 degrees. That means that we get a particular shape of the field around this sphere. So I'll just leave that sentence there for a second. If we look at that, it means that each of the electric field lines that we'd have around this conductor, or this charged conductor, are going to be pointing away from the center of the conductor itself, given that they all exit at 90 degrees. So that would represent our electric field strength there. That then means if you consider that field, what we'll see is that outside the sphere, it's going to appear similarly to what a radial field would look like. So we're going to basically say that it's indistinguishable from a radial field around charge, or around an equivalent charge placed at the center of the sphere. So that means around the outside of the conductor, we're still going to see that equation that we've seen before for electric field strength, E equals kq on r squared. That will still apply around this region outside the sphere. So that's the first important point to note. If we then start to go inside the sphere, this is where things get a little bit more interesting. So inside the sphere, a couple of things to note here. Because the charge is evenly distributed, and second thing to be aware of, so charge is evenly distributed over the surface, and also given that the electric field strength around a charge, so basically we're looking then at the inverse square law. So inverse square law between electric field strength and distance. So due to those two ideas, and just to make a note here, the inverse square law that we're really dealing with is that electric field strength is inversely proportional to the square of the distance. So we've got the symmetry of the charge distribution, and then we've got this idea that if we have, say, a point here, then a smaller distance to that charge, a larger distance to that charge. So combining those effects across the whole surface of the sphere, what we'll see is that the electric field strength inside the charge is zero. Or in other words, there is no electric field inside the charge. Sorry, inside the sphere. Now, if you want a little bit more detail on that, I'll just make a note here. You can have a look at page 412 of the text for further detail of that. So that goes through a much more significant explanation of how that result arrives. So now I want to just have a think about, or have a look at, if we were to graph then what the electric field strength looks like around this charge sphere. So across this axis we're going to have the distance from the center of the charge sphere. We're going to use the symbol R here for a radial distance, and that will be measured in meters. And on the vertical axis we'll have electric field strength, and the electric field strength symbol we use is E, and it's measured in newtons per coulomb or volts per meter, either of those two. Now I just want to make a note up here. If we look at this scenario, we'll note up here that the radius of this sphere, we'll call it capital R, just to make a bit of a distinction between lowercase r and capital R. So on this graph then, we need to be aware that if we look at the limits of the sphere, and if we sort of take to the right as being a positive direction, so we're only sort of looking in one orientation here, so that way we'll treat as being the positive direction. As we go across to the right from the center, we'll see initially that the electric field is going to, well, across the diameter of the sphere, I suppose, the electric field there is going to be zero, and so that's going to be from R to negative R. We're then going to see that outside the sphere, it's going to then follow the inverse square law that we identified before. So we're going to have this asymptote vertical, not an asymptote as such, a discontinuity, where we'll then have the normal shape of the electric field strength curve coming off from there. So notice that we'll have this value across the top here that would correspond to the electric field strength at the surface of the charged sphere itself. So this curve here is going to be that relationship where E is proportional to the square, inverse square of the distance itself. And now coming back to the idea of electric potential, we know that the electric field strength is equal to the potential gradient. So change in potential over change in distance. In this case, we could call that the change in the radius, or the radial distance that we measure. So we know that particular piece of information, but we also know that inside the sphere, the electric field strength is going to be equal to 0. So with those two pieces of information, what we can then identify, if E is equal to 0, so if this quantity is equal to 0 here, the only way that that can be 0 is if that quantity of delta V is equal to 0 as well. So we know that delta V is equal to 0 volts, so the change in the voltage is 0. So that then means that the potential V is constant inside the sphere. So inside the sphere, V is going to be constant. What's the value of that going to be? Well, if we go back to that idea of treating the outside of the sphere as though it's just a normal radial charge concentrated at the center of the sphere, we can then identify that the potential inside the sphere is simply going to be the potential at the surface of the sphere. So remember here that the potential outside the sphere is going to be given by V equals KQ on R. So we'll see that relationship similar to what we saw with up here, that we have this inverse square law outside the sphere for electric field strength. If we sort of continue this graph now, well, not continue it as such, but draw the, I'll leave the same axis horizontally, so I won't bother rewriting the label on the horizontal axis, but the vertical axis is now going to be the potential, and that will be V measured in volts. What we'll see there is that we still have this idea, so if we keep those lines aligned or in the same orientation, looks like that's a little bit out of whack, let me just center that. If we have those two lines still representing the surface of the sphere, R and negative R, that means that we're going to have potential inside the sphere that's constant, and that will be equal to the potential at the surface of the sphere, and then we'll see a decrease in the potential outside, and so we'll have a curve that looks something like that, where that relationship there is going to be an inverse relationship. So there's all of the detail about the potential inside a sphere. Gets a little bit tricky when you start to put it all together. You might need to spend a bit of time going back over it and making sense of how it all links together, or ask me some questions in class and I can clarify it for you then.